Poonam?
Yes, sir, it started.
So, good afternoon, everybody. And we will continue our discussion on predicate logic, which we had started yesterday. And in predicate logic, we noticed that we have been adding a few things from propositional logic, which makes it much more effective for us in order to represent and solve several problems. What we introduced are variables, constants, predicate symbols, two new connectors, and we will say that we will also introduce function symbols. In this class, we will discuss it. And we solved these four problems on the left, and we have had discussions on them. The objective and the plan again is that given F1, F2 and goal, or F1, F2, F3, F4 and goal, after encoding everything, we will try to prove the validity of the final formula. So having seen this, let us see some more nitty-gritties of this whole thing. So let us start solving one by one, each one of them. Let us assume that I have a predicate likes xy to denote x likes y. Now please start writing this one. Please start writing F1. What is F1? Can somebody tell me what is F1?
There exists x for all y and like likes xy.
Is this agreeable to everybody else? Is this agreeable to everybody else? Anybody thinks it is wrong, or anybody else thinks it is right? Soumyadeep Nandi, are you there? Soumyadeep Nandi, are you there? Poonam, can you note down the names of people who are not there?
Yes, so
Okay, sir.
So Soumyadeep, now you are responding. Your yes is for what? You are there. Soumyadeep,
yes, sir.
are you hearing, or are you doing something else in the class?
I am hearing now, so sorry.
See, I would only request you that for most of you, your parents are paying a lot of money. Shubhranil Sanyal, are you there? Shubhranil Sanyal, are you there? Anupam Sharma, are you there? Anupam Sharma, are you there? Manideep Roy, are you there?
Yes, sir.
So is this correct? F1 is correct.
Yes, sir, it is correct.
Then if this is F2, what is F2?
Sir, F2 will be for all x.
For all x,
There exists y
there exists y
likes x comma y.
likes x comma y.
Yes, sir.
Is that okay for others? Nivedita?
Yes, sir.
Nivedita, is this
Yes, sir.
correct?
Yes, sir. I feel it's correct.
Then tell me what is F3?
There is someone whom everyone likes. So there exists.
Write it down and then write it down yourself. Don't think and loudly, so loudly. Write it down and tell me.
Okay, sir.
Devraj Priyadarshi?
Yes, sir.
What is F3?
So I wrote for there exists X such
There
that for all
exists
Y
X
likes
such that
Y,
for all Y likes
Y comma X.
Digvijay Nath Tiwari? Digvijay Nath Tiwari?
Hello, sir, am I audible?
Yes. So tell me, is F3 right or wrong?
Sir, I'm not actually able to see the screen. I mean, I tried to rejoin again and again. So I'm not able to see the screen, but I can tell what I am thinking about the F3 statement.
Tell me.
Sir, so the statement is if everyone everyone likes everyone.
No,
So
F3 is not everyone likes everyone.
oh, sorry, sir. F3 is if everyone likes everyone, then someone.
F3 is not that. F3
So actually,
is...
I'm looking at the YouTube video that you sent because I'm not able to see the screen.
Okay.
So that is why I have actually a bit of
Then
lag in
leave
here.
it. Then leave it. Druhin Abrol?
Yes, sir.
Is this F3 right?
Sir, F3, this, I think is this word F3 is like another form of F2. I think instead of it, there should be only one X for all Y.
There is someone whom everyone likes. So
Yes.
there is one X for all Y. No? It says there exists X such that for all Y,
Yes,
every Y likes X. So what is the problem here?
Is it the same as F2?
Is it the same as F2? F2 says, what does F2 say?
Everyone likes someone.
Everyone likes someone. And what is the can anybody tell me what is the difference between these two?
Nothing.
They are both same. Everybody thinks that both are same.
Sir, but the
Sir,
order in
third
which it is
statement,
written.
No,
That is
sir.
for all
everyone will
life
be
there
liking
exists
only
one.
one person. The second statement, everyone liking any of the any
Here
one of.
it says there is one person, isn't it? I'm elaborating it, whom everyone likes. And what does this one say?
Everyone should like someone.
Yeah, so everyone likes some person, but that may not be the
Person.
That may not be a unique person. I like A, you may like B, somebody may like C. Correct? Everyone likes someone does not necessarily mean that there is a specific person. So this statement F2 that we have written, it is different from F3 in the sense that F2 signifies that for every X, there is some Y, but that Y can vary for different X's. Whereas F3 says that the person who is liked by everyone is the same person. Is this clear now?
Yes, sir.
Yes, sir. Sir, could you please again explain?
When this says for all X F2, F2 says, so let us say there are three people, A, B, and C. For F2 to be true, I will have to say A. So if I suppose there are three people, let me write down. So let there be three people, A, B, and C. For F2 to be true, this makes F2 true. But this does not make F3 true. Is it now clear?
Yes, sir.
Who asked me to explain again?
Yes, sir, it is clear, sir.
So now from these two, what can we write? F3, can we write this or can we write this? Which one can we write? Which one of them is true?
F3 implies
F3 implies F2.
This is true and this is not true. Correct? Is it okay now? Kirti? Kirti, are you there?
Yes, sir. Yes, sir.
This is okay?
Yes, sir.
What is F4?
Sir, one doubt. So the order in which we write for all X, there exists Y, that matters.
Yes, exactly.
Okay, sir.
Exactly. We'll come to the reason why it matters. We'll come very shortly. We will come to the reason why it matters. Let us do these. Then we'll come to the reason why it matters. What is F4?
For all X, for all Y, likes X, comma Y.
Perfect. What about F5?
F4 implies F1.
F4 implies F1. What about F6?
F3 implies likes X, comma X.
Yeah, but F3, you have to make sure that that X is taken throughout in the. So let us rewrite it. So this you are saying, how do I write? What is F3? There exists X for all Y likes YX implies
Likes X, comma X.
Likes X.
Got it? Everybody is clear now? Sorry, this is F6. No? Anybody has a doubt? Alapon Sen? Alapon Sen, are you there? Alapon Sen, are you there? Kinjal Bhattacharya, are you there? Kumbham Sricharan, are you there?
Yes, sir.
So is this okay, F6?
Yeah, yes, sir.
Okay. So now let me just go through the, this looks like a new connector for all that exist. But what is it actually? Just to highlight, for all x, px is equivalent to and of px for all x element of the domain D. Correct? For all is just an and operator, but because it may be an infinite set, therefore it is just an and operator for all elements of the domain. If there is a domain D of which I want to solve, then it is this clear to everybody? So there exists x px will therefore be
Or okay.
Or operator.
So now if you know this, then you can easily write there exists x, there exists y, pxy is equivalent to there exists y, there exists x, pxy, isn't it? Why? Because why? Why are these two equivalent? Because
Dollar and.
yeah, all are or and, but what is the property of all or and?
The order does not matter.
So what is it called?
Associate. They commute.
Commutative.
They are commutative. They commute. They are commutative operators. But if you write for all x, there exists y, pxy, it is not the same as there exists y for all x, pxy. Because and or don't commute, isn't it? They distribute. So it comes just from that formula. The other thing that happens is if I have for all x px and I negate it, what will it become?
There exists negation of there exist px.
It will be this. Not for all x px is the same as there exists x not px. Which law is this?
De Morgan's law.
The name De Morgan's is given because the Britishers wrote this history, or the foreign people wrote this history. But this was discovered even before them in many civilizations, including in recent times. There was a person who worked in the post office in Madras, who a South Indian person who discovered all these laws. De Morgan's has got it later on. In other civilizations also it is probably well known. It's just that The powerful people get to write history. So now this is clear. Now we know that the laws of negation also hold. Any doubts till now? Anybody has any doubts? Krishna Priya?
Yes, sir. Clear.
Go. Now we come.
Sir, one doubt. So in this case, what will be the order of their existence
in
for
which
all?
Case?
In these cases, so like
all of them have been written in the correct order.
Okay.
You switch the order, it will become a problem.
Okay.
Now, suppose we want to write this F1. Then we will define a symbol, predicate symbol, to signify X is greater than Y. And how will we write F1? Somebody help me.
gr x comma y and gr y comma z implies gr x comma z.
Gr x comma y and gr y comma z implies
gr x comma z.
Is this enough?
For all x, y?
For all x, for all y, for all z.
X, for all y, for all z. Good. Now, how will you write F2?
GR person, comma, child.
Here we will need something to specify age. And therefore we will start using a new concept, which is the function symbol. A function symbol is a generalization of a constant. Like a Boolean generalizes to a predicate with arguments, with parameters. Therefore, a function is an extension of a constant with parameters. So I will define a function age x, which will return a value from the domain. What is the difference between a function and a predicate? A predicate pxy is a mapping from d cross d to
0, 1.
True, false. Correct. Whereas a function f xy is a mapping from d cross d to
A constant value.
no, it's a mapping from d cross d to
D.
D. It's a mapping from d cross d to d. Okay. So now once I define a function age, now how will I write f2?
Sir, how is it D cross D to D? I didn't get it. X and Y can be elements of D, but the mapping can be
There
in
is
D.
only one that we will define. Then you can, whatever domains you take a union of all of them and call it D.
Okay, sir.
You take a union of everything and call it D. So how will we write F2?
We need another predicate called child of x is a child of y.
Right, we need another predicate called child. So let us write it as CH XY, which says X is a child of y. Now write down F2.
For all x, for all y, if x is the child of y, then x's age is greater than y's.
For all x, for all
y
y.
is greater than x's.
CH of xy implies GR age of y comma age of x.
Clear to everybody? Is it clear, everybody?
Yes, sir.
Yes, sir.
I won't do F3. You can do F3. It's easy. What about F4? What else do you need to do F4?
Functional symbol sum.
I need one more function symbol sum. As a practice, we are writing the propositions, variables, and the predicate symbols to start with lowercase, and constants and function symbols to start with uppercase. So sum xy will be, and then you can write it. So that is something I will leave it to you to do. I want you to answer this question. I've written a formula. For all x there exists y, px implies for all x rxy. Now this y obviously is unique and corresponds to this y. Which x corresponds to which x?
Rx.
This x corresponds to this x.
Yes. The px.
And this x corresponds to this x. These are similar to, in programming, they are similar to the scope rules that we use in structured programming.
So shouldn't the outer x be defined for the whole of the expression?
It is defined for the whole of the expression. But it
Why?
is like when you define local variables, you define a structure x. When you define, you write C programs, right?
Yes.
So there you define an integer x and then you go and open another curly bracket and write another integer x. And then when you write this x, it corresponds to the local reference, right? The scope rules define it.
Yes.
So here also like that. Suppose I had written for all x, there exists y, px implies for all x, r x y implies wx. Then this x corresponds to this x, this y corresponds to this y, And this x corresponds to this x as well as this x. All right.
Yes.
So the scope rules are also to be considered very carefully. Any questions here?
Sir, in F1, where you have written F1, so you haven't given a bracket. I mean,
Yeah, then that you can. I have not given a bracket, but this is supposed to be like this. Because they are all unique, so I've put it all outside. Now, suppose I write down what I've written down here. For all x, px implies qxy. This x obviously now I know corresponds to this x and corresponds to this x. What about y? What does y correspond to? What does y correspond to here? Anybody?
Any y.
Love Singh, are you there?
Yes.
What
Yes, sir.
does this y correspond to? Did you
Sir,
get a
not
chance to watch
yet.
the video and come? Did you get a chance to
Sir,
watch
I'm
the
not
video and come?
able to hear your voice properly.
Did you get a chance to watch the video and come? Can you hear me?
Hello.
Can you read the screen?
Sorry, sir. So wait a minute, I'll rejoin.
I think, people are not even bothered whether they are hearing, whether they are, all this fighting that I try to do is all useless. Coming to class, pre-recording lectures. He must be watching some movie. Suddenly heard me call him. He thought. Little John Saronia, are you there? Little John Saronia, are you there? Mahajan Rohan Raj, are you there?
Yes, sir.
So tell me, this y is where? What is the state of this y?
I think it is any element from the domain.
Yeah. So did you watch the video and come? No, you couldn't. So this
Yes,
is
sir,
called
I couldn't.
This is called a free variable. All right. Those variables which are connected by quantifiers are called bound variables. And those variables in the formula who have no connection with any quantifier are known as free variables. Got it? Hello, did you get it?
Yes, sir.
Okay, thank you. So now we come to certain terms and terminologies. The first term are we know what are variables. We have just seen what are free variables, what are bound variables. We have also seen what are proposition symbols, what are constant symbols, what are function symbols, what are predicate symbols. We have seen that variables can be quantified in first order predicate logic for all x px. But symbols cannot be quantified in first order predicate logic, which means we cannot write something like this. For all p, for all x, px. This is not possible in predicate logic. That means in predicate logic, we can quantify the variables, but we cannot quantify the predicates or the functions. Quantification of predicates and functions can be done in what are called higher order logics. But predicate logic is very, very powerful. It is very powerful in the sense that it is equivalent to whatever can be computed by a Turing machine. That is its power. Now we come to the most important thing. We know that a formula is valid if Mansi Mukund Bandhavkar, are you there? Manasi Mukund Bandhavkar. Mayank Sonu, are you there?
Yes, sir.
So a formula is valid if it is anybody would like to suggest if it is true?
For all interpretations.
If it is
For
true
all interpretations.
For all interpretations. Now in propositional logic, an interpretation can be created by assigning true false values to the Boolean variables. But that is not so straightforward in predicate logic because there are so many other things. Other than proposition symbols, we have constant symbols, we have function symbols, we have predicate symbols. So how do you define an interpretation? This is very critical. It is important for you to grasp what do we mean by an interpretation. So to define an interpretation, our first thing to do is to define a domain. So for any interpretation, we have to first define a domain D. Then map every propositional symbol to, can anybody suggest? So every propositional symbol, like in a truth table, we have to assign it to true or false. Then map every constant symbol to, can anybody suggest what to do?
Domain.
Yes, to an element of D. Map every predicate symbol of the type P x1, x2, xn as D cross D, sorry. And finally, map every function symbol of the type f x1 to xm as, so here we have taken n values. We will take m elements to d. So we have to create such an interpretation. So to create such an interpretation, once we create such an interpretation, we will know whether the formula is true or false for this interpretation. So let us take an example. Let us take an example. Our example is what? We had this Mary goes to whatever, no? We had for all x, that Mary case. So in the Mary case, let us, that Mary problem. In that Mary problem, let us define a domain. Tell me any domain you want to define. You know that Mary, lamb, all those are symbols. Tell me an arbitrary domain you want to define. Let us define Rasagulla. Let us define some domain like this. Good. Rasagulla, Sandesh. What else? Dosa. So R stands for Rasagulla. S stands for Sandesh. D stands for Dosa. Is it okay? Everybody is with me?
Yes, sir.
Yes, sir.
Good. Now, what are my constant symbols? Mary. Let me map. Tell me where you want to map Mary to. Lamb, where you want to map? Tell me, anybody, just tell me.
Yes.
Yes. And school you want to map? Again, you can choose any one of them. You don't have to choose one which is not chosen.
D.
Yes.
Okay, let's choose D. Somebody we have chosen D. Now, what else we have to define? Goes XY. So we have to define where goes are true. So we have to define goes RS, goes RR, goes whatever. All of them. How many will be there?
8.
8.
9 combination.
9 combinations. Let us for the time being say that goes, let us just for these 9 combinations, let us choose a combination and let us say that goes XY equal to true if X is equal to Y. Let us say, and equal to false if X is not equal to Y. Let us say we have chosen this. We can choose whatever we want. Are you all with me? Please concentrate. Are you all with me? We have chosen one interpretation. Now, what are my formula? I have F1 as for all X goes. sorry, for all, what was my formula? What was my F1, F2, F3 in Mary? For all X, for all Y. Somebody help me.
For all X goes Mary X implies goes lamb X.
F1. F2 was goes Mary school. And goal was goes lamb school, right? Are you all with me? Or lost? Anybody who is lost?
Excuse me, sir.
Yes.
Sir, in F1, why do we need to put for all Y?
Sorry, there is no Y. For all X goes MX implies goes LX. You're right. Are we clear? No Y, no Y. I made a mistake. Now is it clear to everybody? And what will I have to prove? F1 and F2 implies G. Now under this interpretation, is F1 true? Under this interpretation, is F1 true or what?
False.
True. F1 is false.
True.
F1 is true or false?
True.
True.
For F1 to be true, then what must be true? If F1 is true, then what will be true? So person who said false, can you tell me why why it is false and not true? Because goes goes DD. I have mapped Mary to D. Goes DD is true or false? Based on this definition?
True.
True.
It says goes DD must mean goes. This is what it means, right? Under this interpretation, are you all with me? I have mapped M to D. Correct? Are you all listening?
Yes, sir.
Yes, sir.
Yes, sir.
M is mapped to D, right?
Yes.
So I have put this to D. Since it is for all, it must be true for every case where goes D, where goes D, S, where goes D, R. It must be true for all cases, right? So, but this part is true because I have defined this to be true. Goes XY is true if X is equal to Y. But will goes SD be true?
False.
This is false. So this part of this formula will become false. Therefore, this formula will become false. So F1 will become false. Is it clear to everybody or not?
Yes, sir.
So if
Yes,
F1 becomes false, this formula becomes true. F1 and F2 implies G becomes true. In this case, F2 is false or F2 is true?
False.
And
False,
G is true or G is false?
Sir, true.
G is true. L is mapped to S and school is mapped to D. L is mapped to Sandesh and school is mapped to Dusa. How can it be true?
Oh, sorry. Yes, sir.
So F1 is false, F2 is false, F1 is false, F2 is true or false?
So true.
True. And this one is false. But because it is like this, this formula becomes true. And now you try any other mapping of Mary Lamb School to this domain. You try any other combination of defining the goes predicate. The formula F1 and F2 implies G will always be true. You try to define a different domain, call a new domain D equal to set of odd numbers, and then map M to somebody, L to somebody, school to somebody, define a new goes function. Whatever you do, you will always find this formula true. So the number of interpretations now can become infinite. And because the number of interpretations becomes infinite, the algorithm to prove validity is a very, non-obvious algorithm. So we have defined interpretation, and once you define an interpretation, now you know a formula is said to be valid if it is true for all interpretations. A formula is said to be satisfiable if there is some interpretation for which it is true, etc., etc. Our objective is that given first order predicate logic, how will we prove validity, satisfiability, etc. And how we do that will come in the subsequent classes. Before I close, I want you to pay attention to this formula. This formula, is it in first order logic or not?
No.
Why? Because a predicate has been quantified. But so this is in second order logic. But this formula is a very interesting formula. It expresses something which we have all studied. Can you tell me what it is trying to express? Anybody?
Induction theorem.
Yes, principle of induction. If you map P is the principle which I want to prove, inductive principle. P0 is the basis condition. Then it says this is the inductive condition. And this is the final result. Are you getting an idea how this is the inductive principle? It says that if it is true for 0, and if Px is true, then P of successor of x is true. Then for all y, Py is true. I will not get time, but you please watch the video to see a discussion on this, and we will try to talk about the limitations and Russell's paradox in the next class. So we'll stop here. If there are any questions, I'll try and answer them. But I will again recommend, please watch the video and come.